All right, this is a good question. We're going from grams of a molecule, it's like a sugar molecule, to atoms of just oxygen. So not only are we gonna have to convert from grams to moles, so we live in moles, right? Chemistry is done in moles. It tells us how many molecules are going on. Then the conversion is not just moles to atoms, but we have to do a mole ratio. How many moles of this molecule compared to moles of oxygen? And then we can go to atoms of oxygen. So we're going to do a conversion. So here's my unit plan. So I'm going to say grams. I'm going to write out the whole things to moles. Now here's our mole ratio, because now we're going to moles of oxygen, and then we're going to atoms of oxygen. So there's my unit plan. Now this is this new stuff that we're learning, these mole ratios, because here we're going periodic table, molar mass. Here we're using our formula, our molecular formula. And then here we're using Avogadro's number. Now, keeping them, doing them correctly is important. So this part right here is kind of like I mentioned, where 1 mole of cars would have 4 moles of wheels, right? So we can have more moles of a part of the whole than we do of the whole. And so here we're going to look at how we have for every 1 mole of this molecule, we have 6 moles of oxygen here. We get 72.06. Then we got H12. I'm going to go 1.01 times 12, 12.12. And then we got 06, 16 times 6, 96. And so we add that up, 0.18. We got 96 plus 72 plus 12, 180.18. Now that is grams per mole. Those are 2 units. Remember, I can write 180.18 grams per 1 mole of what? It's important to clarify moles now because we have moles of different stuff. Or I can flip that and write that on top like I'm going to do up here. So I'm going to get out of grams, so 180. Now it's important to separate those double units. Don't write grams per mole over 1. That's not right. That's not what we're doing. The grams are on top and the moles are on bottom, or the moles are on top and the grams are on bottom. So now I'm in moles of C6H12O6. So I'm going to say every 1 mole, I'm going to get out of that, has 6 moles of oxygen. There are 6 oxygen atoms for every molecule, or more, the official way to say it is there's 6 moles of oxygen atoms for every 1 mole of this molecule. Then I'm going to say every 1 mole of oxygen has 6.02 times 10 to the 23rd atoms of oxygen. Now remember, that's 1 mole has a bunch of atoms, not 1 atom is 6.02 times 10 to the 23rd moles. So getting that right is correct. So now I'm going to multiply everything on top, divide everything on the bottom. So I'm going to say 10 divided by 180.18 times 6 times 6.02, and I'm going to use my EE button to the 23rd, and I 2.00 times 10 to the 23rd atoms. We're going to go 3 sig figs. So 2 times 10 to the 23rd. 2, don't forget your 0.00. So even though it's zeros, those zeros are significant. There we go. So they got a slightly different answer, likely because their molar mass is slightly different. They got 180.16, I got 180.18, a little bit different rounding. And so that ended with a slightly different answer, but considered it correct because it's within that range. So there we go. So this is dimensional analysis at its finest. Remember, we learned this process so that we could use it when these problems get difficult and we're using the language of chemistry.